Thanks very much to the organizers for putting this together. I think that there's a lot of important issues that are being discussed, and I like that it's being done in a very sort of systematic and careful way. So this is great. All right, so one of the things that I noticed in this particular group is it is very diverse. There's people coming from control theory and from systems engineering and AI and policy and all sorts of things. And I decided that from my perspective, Emma mentioned this as well, safety and control, artificial intelligence, what are safety and control? Like, they mean something to me, but is this what it means to the rest of this diverse community? So I did what any scientist would do. I did research, and I asked my Facebook friends what that meant. I said, here's the title of the workshop. What do you think the workshop's about? And so one person said that it's about AI applications, applications of AI to control systems to make them more safe. But that was really good. But really, that was the workshop that happened in DC about social impact, positive social impact from AI. So that's not really what this one's about. All right, then another possible topic that this could be about is about systems, designing AI software that makes complex intertwined decisions, control, that's going to be robust to bugs and hacking to avoid unintended harm, safety. And I think that has been about that. I like that one of the people, one of my Facebook friends, just sent me the image of Homer Simpson. That was, it's like, what do you think this means? And he said, this image, which is not, that's not a bad sort of viewpoint to have. I feel like that is pretty well covered, and people are talking about that. And another interpretation of these words, safety and control, is kind of a notion of ethics. A lot of people said, like 7 of the people said, implementing something akin to Asimov's laws, control, for guiding AI systems towards beneficial decisions, safety. So how do we encourage AI systems to do things that we really want them to do and not do things that are harmful to us? And then most people said things related to superintelligence. So we need an e-stop, an emergency stop, the big red button, to stop AI systems that have transitioned to rogue status. And Skynet and HAL were specifically brought up by my otherwise intelligent friends. So, I really, really want to spend my time talking about that, because this is an issue that keeps me up a lot. I get a lot of questions from people about, why is it that I'm working on the thing that's going to kill us all? And I really, really don't think that this is a good way of thinking about things. I think the fast takeoff into superintelligence is a cool idea, but not reality at all. But I'm not going to talk about that any more than I just did. Instead, what I'm going to do is focus on a thing that kind of cuts across. So even if you don't think that superintelligence is going to emerge very suddenly and start to take over everything that happens, when you talk to people who do believe that, the problems that they say are important to think about now are actually pretty much the same problems that I think are important to talk about now, even not believing in that. And a lot of it comes down to this notion of values, of how is it that an AI system can evaluate the states of the world and prefer good ones and avoid bad ones. So I want to highlight this notion that rewards are really a critical concept in lots of what AI is doing. Lots of flexible decision making comes down to the idea of systems that are going to consider different possibilities and then choose the one that has the highest score. So just as some concrete examples in information retrieval, like what Google does or what Bing does, when you give it a query, it scores all the pages that it's searched on the web and then returns you the ones that have the highest score. So that score notion, it doesn't have a rule that says, oh, if this is the exact query, then you really want to answer in this kind of way. No, it's got a scoring function, and that scoring function drives the behavior of the system. Same thing happens in machine translation. So when you type in a thing in French or whatever and it comes out in English, what's happening underneath is that a system is scoring alternatives and returning the one that's best. My research area is in sequential decision making, so things that are more akin to like chess and Go, game playing. And these also have that same kind of property to them. These systems don't have specific rules that say, when you're in this situation, do this thing. What instead is that they think about all the different decisions they could make, what the implications of them are, and then score the different possibilities, and then behave in a way that maximizes the high scoring possibilities. So I like to think about this sort of casually as free will as a software design pattern. Like, what we're trying to do is make systems that are actually choosing among different possibilities to accomplish a goal. So they enumerate, they evaluate, and then they select. I'm reassured by or assured by people who actually are more philosophically minded than me that I have absolutely no idea what free will means. But from my perspective as a computer scientist, I feel like this is a really good way of thinking about it. And of course, in all these systems, the choice of scoring function matters a lot. That's going to actually drive what the system really does. And so I like to think about these problems in a framework called the Markov decision process framework. It really just gives us a concrete and formal way of thinking about states of the world, actions that can have an impact on the world, and this sort of reward notion that comes back to provide something for a system to actually maximize. I'm going to, just to demonstrate this for you, here's a little environment that comes from the classic AI textbook by Russell and Norvig, where we've got an agent, this gray thing, that's moving around. It can go north, south, east, and west. And it gets a +1 for ending up at that red square, and a -1 for ending up at that blue square. And so really what we see, the environment is such that it's a little bit slippy. So even though it's trying to take a direct route to red, right about there, something surprising happens, but it adjusts to it and then continues. So this is a great example where if we were just deciding on the behavior of the agent to say, oh, you should go north, north, east, 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 that wouldn't work in this case because at one point something surprising happened. The system has to actually adapt to that, or at least respond to it. And so, so we can, if we formalize these kinds of problems as a Markov decision process, there's a bunch of algorithms that we've got that can actually turn that specification, the reward function in the environment, into behavior that we think is good behavior. And rewards are great because we can put positive rewards on things that we think are good and negative rewards on things that we think are bad, and we can express, trying to go to a place or trying to accomplish something while avoiding something else. So this is actually really cool. But it turns out that setting rewards effectively is extremely hard, and there's a whole bunch of reasons for this. There's some cases that are actually really crisp and easy, and I don't think there's a lot of debate about whether this is a good notion. Things like if you're trying to have a system that's maximizing money and that's all it's doing, then money is a really good reward signal. If it's trying to minimize time, then time is a really good inverse reward signal. But often, in systems that we care about, it's not so clear. So if we want our thermostat to balance comfort and cost, like what are the units of comfort and cost that make it so that you can, definitively say, here's what the reward function is, now maximize it. So usually what happens is people will sort of tweak it, like, well, comfort's worth this much and cost is, negative this much, and so now maximize. And that's not the only problem. There's lots of other problems as well. The rewards, even if you have a perfect notion of what reward is, like -1 for global warming, and you're trying to make your house work well, that turns out to be a really hard signal to learn and plan about. Like, exactly what should I do now to avoid -1? I don't know. I need a little bit more guidance. It's a computationally too difficult a problem. Rewards can sometimes be not expressive enough unless you expand the state space, and then you get this problem of unintended consequences. So here's a classic example from humans. At one point, I think there was an area that was overrun by cobras, which seems like that's a big problem as far as I'm concerned. And so the government stepped in and they said, we're going to get this under control. People, kill cobras, and then to encourage you to do that, because who wants to mess with a cobra, we'll pay you +1 if you bring us a dead cobra. Now what this actually led to was people breeding cobras so they could kill them and then get the money for it. Now this caused exactly the opposite to happen than what was supposed to happen, which is now there was way more cobras around than originally. And so setting rewards, even if you've got people in the loop, setting rewards, mechanism design is an extremely hard problem. So here's a more reinforcement learning-y looking version of the same thing. This is not exactly cobras and so forth, but here what we're trying to do is I would like the little gray robot to navigate to the red position without touching blue, all right? And so the way I do that is I give it a big +1 for getting to the red region and a minus something for stepping in the blue. And what should that something be? Well, it turns out if we set that something too low, then the system's like, I don't care about that, I'm just going to go straight to the goal. And if I set it too high, then it's like, I'm so afraid that I'm going to slip and fall into blue that it's better that I just cower in the corner and avoid engaging with the world. And so it turns out to be really hard to get those numbers exactly right so you can get the behavior that you want. You can see it's still now running, like it's pushing itself into the corner and occasionally slipping away and then going right back to the corner. So this is, it's doing what we told it to do, but what we told it to do is not really what we wanted it to do. So, and in this particular problem, it turns out as the slipperiness probability of the floor changes, exactly how you want to set that penalty shifts. And in fact, there's some slipperiness values for which there's no way to set the penalty to get the behavior you want. So, rewards are great things. They give us the ability to express lots of kinds of desirable behavior. They're automatically optimizable. We've got tons of algorithms for this. But they seem to be kind of brittle. They can be very complex to specify. Planning can be difficult if they're too far, if the rewards are too far away, and there can be these unintended consequences. So what I'm going to try to do is summarize 3 methods that I've looked at for trying to avoid these unintended consequences, to try to make the behavior that we want come out without having a person have to nail down what all the rewards are. I'm going to talk about logical specifications of behavior, norm learning via inverse reinforcement learning, and human-mediated rewards. So the first thing I want to talk about, and this topic's very close to this, were touched on by some of the other speakers, is the notion of saying, well, we're not going to just throw rewards at it and sort of see what happens. We're going to say what kind of behavior we want. We're going to be able to express that in a formal way. There is a language of sequences that's been studied now for a number of years, known as linear temporal logic. And the idea of linear temporal logic is we're going to put constraints on what the sequences need to be. So it turns out that it's a pretty good match for the sorts of things that we express with rewards in the reinforcement learning community. So the far left thing is a problem, classic sort of test problem known as mountain car, where the goal is for the car to get up to the top of the hill. And typically the way that we do that is we'll put little minus rewards for not being at the top of the hill, and then let it maximize. Instead, if you want to specify this in terms of linear temporal logic, you might say something like, eventually be at the top of the hill, which is really the same thing. It's the same thing that we're saying with rewards, but it gives us a kind of a nice formal way of saying it that we can actually generalize to lots of other kinds of tasks as well. So the cart pull task of let's try to keep this thing balanced without it falling over, we can say as forever don't drop, right? Don't fall over. But we can also start to put these things together in interesting ways. So the little grid world that I showed you before, we can say, well, we want it to go to P, but we don't want it to hit Q. One way to say that is don't go to Q until you've reached P. And if we actually set that problem up and then optimize, we get the behavior that we're looking for. Similarly, Tom Dietrich gave us the taxi problem a number of years ago, which we just can't get enough of. And the taxi problem says that we want a taxi to go pick up a passenger and then drop it off at its destination, and we can say this in logic too. Eventually it should be the case that we're picking up the passenger and from there eventually dropping the passenger off. So we get a nice level of expressivity, and it actually, for this little grid world thing, it actually causes it to do the right thing, which is very satisfying. So I told it, don't queue until P. So don't hit the blue until you get to red, and it works, and it's independent of the slipperiness value of the environment. There's no reward tweaking that I have to do. It just did the thing that I asked it to do. So this is great. Specifying behaviors instead of rewards gives us a certain amount of expressivity. You can automatically optimize them. It's robust to changes in environments that in a way that rewards aren't. But it's still complex to specify. Planning can still be very, very difficult. It doesn't help with the Cobra problem. Few things do, but it doesn't really give us a way of saying things at exactly the level that we'd like. So I want to talk a little bit about inverse reinforcement learning. So reinforcement learning is this problem of given a learner, given something that's going to behave in an environment, if we give it a specification of rewards and the environment, it can generate behaviors. That's regular reinforcement learning. Inverse reinforcement learning, we're going to switch the direction of the arrows. And we're going to say now what we're going to do is we have a learner that we're going to show behavior to and give it an opportunity to interact with the environment, and it's going to figure out what the right rewards are. And so this is kind of a cool idea because we don't have to specify the rewards. We can actually let them be learned. Here's a quickie concrete example. If I show you this behavior and I tell you that there's rewards sprinkled in the different colors, you might conclude, well, blue doesn't look so good, green looks really good, orange we can't really tell because we had to go through orange to get to green, and red apparently isn't really very important to us one way or the other, or we would have gone around it. And inverse reinforcement learning algorithms can discover exactly that. From that one trajectory, it can work out what's good and bad, and it can do the counterfactuals to figure out, well, if this had been good, you would have done this other thing, so it's probably not good. We're using this now in the context of norm learning, trying to get a system to figure out which things it should prefer to be able to interact well with us in the environment. All right, so there's some good things and bad things about this. and moving on. So, sorry. The last thing I want to mention, apparently extremely briefly, is human-delivered rewards, this sort of idea that, well, maybe we don't want reward functions at all. We want people to say, that was good, that was not good. It turns out that when we ask people to do this, to train reinforcement learning agents, they act in a way that's very different from our standard reward functions. They tend to give feedback on actions. They tend to mean different things when they don't give rewards, depending on the person. The amount of explicit rewards that they give tends to decrease over time. So even though the system did something that was good, a person might not actually reward them or punish them for it because they should know it by now. If you actually run regular reinforcement learning algorithms on the feedback that people give, they don't work well at all. They don't fit. So what we've been doing is actually taking a cue from how people train animals and how people think animals respond to feedback, and running studies where we actually have people give rewards to fake animals, cute little puppy animals, and from that kind of have worked out a new set of algorithms that actually respond much better to human-delivered reward than the classical reinforcement learning algorithms. And we're training robots that way. All right, so the high-level conclusion is that even though rewards have been very good to us, we maybe want to be kind of careful using them for systems that are going to interact with people in the future. There's alternatives that are needed. We just looked at a couple so far, but there's a lot more out there to do. So thank you very much.